This is cold spray additive manufacturing. What we're doing is taking high pressure compressed air at about 500 psi or 30 bar, and we're moving that through a converging diverging nozzle, like a rocket nozzle. In that process of moving through the nozzle, the air accelerates to about Mach 3, and then we introduce a stream of metal powder particles into that flow. And they're going so fast that when they impact the substrate plate or the parts as they're building up, the kinetic energy of that impact causes them to fuse into dense metal parts.
This is an unfinished part?
So this is raw as it would leave the printer. This actually has a heat treat on it. And then here we see the kind of rough oxidized as printed surface. We can machine that away and reveal this nice, lustrous, dense metal. It's the same technology that you came and saw last year, but now we're doing it in a bigger system. This is the WarpSPEE, where last year was the Lightspeed. This machine actually has a 1 meter diameter working area and can build parts over 1 meter tall. Our core validated materials are aluminum 6061, copper, 316 stainless steel, and there's a couple bronze variants, which are alloys that contain a lot of aluminum, copper, and other alloys.
Nickel, aluminum, bronze. What's special about this material and what drove the consumer need for it?
There's a lot of marine applications for nickel, aluminum, bronze. It's very corrosion resistant, in addition to it being very tough. So it's great for anything that might involve seawater, pumps, underwater applications. It's also very tough and naturally lubricious, so it will contain lubricants in them to have low friction and low wear for certain applications, which is why we have the bearing or the bushing that's in your hand.
I've toured a couple large ships and got to see their machining centers because, you know, when you're out at sea, if something breaks, you need to be able to fix it. It's a really good example of when you would need to additively manufacture a part.
Yeah, absolutely. And the other thing is, like, even if you could machine it at sea in a traditional sense without an additive solution, to make a bushing like this, you would need like a 12-inch diameter solid rod. And then you'd have to cut all of this out into chips and all of this material out into chips. And so you'd be spending potentially days machining all that out of a giant solid rod, which you need to carry around, move around, and that's not very practical. What's nice with us is with about 20 kilograms of material, we're able to produce this, and that's just in raw powdered form. So it's easy to move around, easy to become any shape that we want. The same amount of time that powder became this shape, it could have been made into this shape. This is a strut to guide a prop shaft as it protrudes off the bottom of the hole, so the prop shaft is spinning, and this is sort of a support. Lastly, we have this cam lock fitting. So one jug of powder could become any of these shapes, and that's what's really nice about it. Instead of carrying a block that's the size of a shoebox here, a round bar that's, you know, maybe 6 inches in diameter but 12 inches long, and then a 12-inch diameter bar that's 4 inches long. Those would all be different billets if you were trying to machine these from scratch, where with a cold spray type solution, we're just carrying raw powder that can become any of these shapes. This right here is an adjustable pitch propeller body. There'll be blades that go into each one of these holes, and then they can actually be mechanically actuated to control basically the efficiency at certain speeds, right? And of course, it's a saltwater environment, so the corrosion resistance for that application is very important. That part is about 32 pounds, and it will build on our machine in just over 4 hours.
Oh man, that's really fast.
That's a bushing, so think of like on a big crane boom or something like that, the wear surface, that would be pressed inside of a large fabricated body, and then a pin would be slid through there, and that's where the friction bearing surface of, you know, a big mechanical component would be. It's a great material for it because it tends to be low wear, and again, it's naturally lubricious, so it holds on to the lubricating materials, so that way it has an extended wear life.
We took a look at the Lightspeed last year. Then you had the WarpSPEE, which is, I'd say, significantly larger. And now, I guess this is even bigger. Well, technically, this could fit on the WarpSPEE, a part of this size.
It could fit, but the problem with the WarpSPEE, if we look at that, is the robot was holding the workpiece before.
Okay.
And the robots are limited with how much mass they can move around effectively and quickly and accurately. And so that's been a long limitation with our older system configurations, is that the nozzle is fixed and the robot is holding the part.
Okay.
And so with even the WarpSPEE here, there's actually a 40 kilogram limit of payload that the robot can handle. And so what's so exciting about this is we kind of shift that paradigm around, and if you look at that picture there, you'll notice we incorporate the spray nozzle onto a robot arm, and the workpiece itself becomes stationary on that turntable there. And what that means is we're now no longer constrained by the mass of the robot, because we can build parts onto that could get into, multiple tons of material.
Wow.
And that's what this part is here. If you try to lift this thing, you'll notice that you're probably not strong enough to do it alone.
Yeah,
this is copper, so it's very dense, very heavy, and a part this big is far too heavy for a regular size robot to wield around and whip around quickly like you saw when we were building the sample part earlier.
Right, this one you really gotta lift with your legs. And then how much did this one weigh?
So this part here is about 100 kilograms, so much beyond what the payload of a normal robot could be. As you think about it, we are dealing with metals. Metals tend to be dense, so it's really a natural evolution as people want to build bigger parts that quickly run above the limit of a robot payload at just 40 kilograms.
Would this still be a machine that you're targeting to embed onto a ship or a mobile platform, or is this more of a stationary?
So as it is today, we just announced this technology within the last couple weeks, but we're really working with industry partners to see how it evolves and see how people demand to use it.
Right.
It is a big, heavy machine, which is probably why it didn't make it here to the show.
Oh yeah.
It would be, almost as large as the whole booth here. If you look at the, containment room, that's our CEO and founder sitting there on the build plate. So you notice, compared to a normal person, it's just a massive scale. The build rates are pretty astounding, where I believe this whole part on that machine built in about 12 hours.
Oh my.
So it still does a pretty good job of keeping up. But one of the things we're working through is how to hold that much powder in a hopper. We can build potentially hundreds and hundreds of liters of powder volume in a single build now, and our normal powder hopper is limited to about 10 liters.
Also, I noticed the platform that he's standing on is it has slots in it. It looks like a CNC rotary stage.
That's pretty much what it is. It's a large adapted version of something similar to that. So these here are set up to be able to mount various fixture plates inside of there. This one is about 600 millimeters by 600 millimeters. But as we do larger parts, we'll need to fixture and clamp the build plates down for those.
So I noticed there's a bunch of dots on here. Can you explain what that's about?
Yeah, so these are just target dots for a handheld scanner. We just are trying to, as we're developing this machine and the technology, have a good understanding of how accurate it is and what the tolerances would be expected. So we worked with one of our vendor partners to throw some stickers on and just get an accurate scan of the model after it was printed.
In terms of a slicer for this, it's not the same as like a Prusa slicer based system.
It certainly is different, and it's something that we've developed in-house, but conceptually it works very similar to an FDM style or Prusa style slicer. We're going through on an interval, slicing through the model. That gives us a bunch of 2D profiles. From there, we develop tool paths, which are contour work where we're spraying at a 45-degree angle.
Oh, yeah.
And then once we get the inner and outer contour, we do a normal spray and a raster pattern to fill in the boundary. So where our software really takes over in the customization is converting those movements to the 6 joints on the robot, right? So to be in a specific place with a specific orientation requires a combination of movements of all of those joints, and that's where the complexity of the software that we've developed really comes over. But the general approach, get a profile, contour it, fill it, that's the same, and then we just convert that through a series of complex translations to actual joint movements and velocities.